Okay, so let's do a practice inclined plane problem. So we have a 75 kilogram box and it's sliding down a 25-degree ramp with an acceleration of 3.6 meters per second every second, or meters per second squared. So what is the coefficient of kinetic friction between the box and the ramp? Now again, this is one of those problems that we're given this answer, but the question is, can we figure out how to get the answer? So I have part of my picture drawn over here. Let's go back over and let's fill in a little more info. Some things we know. We know that theta, our angle right here, is 25 degrees. And we know the forces that are acting on this. Now, we know the force of gravity always acts down, straight down. We know the normal force is going to act perpendicular to the surface, and it shouldn't be quite as long as the force of gravity. I don't know if I did a good job of representing that or not, but it shouldn't be quite as big. Because remember, we're going to split the force of gravity up into components. Now, what's happening is we don't have any force pulling directly down that we could see, but we do know there's kinetic friction. It tells us that in the problem. So we have some kind of a force acting up the ramp that's going to oppose motion. So remember, when we do our coordinate system, we just basically are shifting the whole coordinate system so that our x is running parallel to our surface, and our y is running basically parallel to our normal force. So again, this comes down to, it's up to you where you want to put your plus and your minus. You can put, if you want to put down as positive or down as negative, that's up to you. I'll go ahead and put down as positive here on the left. Here's my negative, there's my negative, there's my positive. So hopefully that's clear for you. The x and y, I think, are making that a little difficult to read. But anyway, let's take a minute, and we should probably take this particular box and we should break up this force of gravity into components. Now remember, here's the deal. We wouldn't have to break force of gravity into components if the force of gravity were lying nicely within our coordinate system, but because we took the whole coordinate system and shifted it, that means we've got to take gravity and break it into components. So we're going to bring it down here. I'm going to redraw my force of gravity. I'm going to redraw it a little bigger. And I'm going to break that into two different components. Actually, let me get rid of where I labeled this force of gravity real quick here. I want to make sure it fits into my existing coordinate plane, so I'm going to go ahead. That's going to be one leg. Here's going to be the other leg. So down is going to be force of gravity in the y direction, matches up with my coordinate system, and across is going to be force of gravity in the x direction. And this, although it's somewhat painful, is supposed to be my right angle triangle here, because these are my two legs. I don't think I drew this really well. Let me see if I can't clean this up a little bit so it's a little clearer where our right angles are. So again, if I run parallel to my existing y-axis, that's force of gravity in the y, coming down here, force of gravity in the x, my right angle, and then here is my force of gravity. Okay? So we're going to deal with this theta, and remember, basically we have a right angle right here. So if this is a 25-degree angle, that means this has to be 90 minus 25, which, as you know, should be 6. I'm having a minute here. 90 minus 25 is going to give you 65 degrees. So if this is a 65-degree angle, that means the angle on the other side here, if we'd make it a 90-degree angle, has to be 25. So again, we're working with a 25-degree angle right there. So what that means is, if we're going to figure out force of gravity in the y and force of gravity in the x, that should be pretty simple if we know what the force of gravity is. And we can find that. Let's go ahead and write our F-net equations now. We've got our net force in the x direction. That's going to be force of kinetic friction plus force of gravity in the x direction. And in this case, this is important. There's an acceleration, and the acceleration is in the x direction, so this does not equal 0. So we'll come back to that. The other piece of information that we can identify is that in the y direction we have the force of gravity, the forces in the y direction are force of gravity in the y but also the normal force. So we'll say normal plus force of gravity in the y. And in this case, we can say they are equal to 0 because we're not moving up or down, not levitating. So we can say, okay, the forces here must be in equilibrium, so it must be equal to 0. So some things we know. We know mass is 75 kilograms. We're given that in the problem. We also know force of gravity by definition is mass times acceleration due to gravity. So if you take a minute and do the math on this, the force of gravity is going to be 75 kilograms times 9.8 meters per second squared. Now you're probably saying, why didn't you make it a negative? Again, at this point, you could think about it like I'm just finding magnitudes. You're going to be expected to assign signs, but for now, I just want a number. So I have 735 newtons, and it's going to be in the negative direction, or down. But we're going to break it apart, okay? So, force of gravity in the y direction. Separate a little here, because now we're going back to our vector and our resultant vector and our vector components. Force of gravity in the y direction is going to be equal to, if my angle's 25 here, I'm given, for adjacent, the cosine of 25 degrees equals adjacent, or force of gravity in the y, over force of gravity, which is 735 newtons. So that means force of gravity in the y equals 735 newtons times cosine 25 degrees. And that should equal 666 newtons. So that is force of gravity in the y direction. We can also find force of gravity in the x direction by doing essentially the same thing. Except this time instead of sine we're using, instead of cosine we're using sine because it's opposite. So sine of 25 degrees equals force of gravity in the x direction over 735 newtons again. So we have 735 newtons times the sine of 25 degrees, because we're multiplying on both sides to cancel it out over here in the denominator, equals the force of gravity in the x direction. So the force of gravity in the x direction is going to be equal to 311 newtons. And again, I would say if you're not getting the same numbers I am, check your calculator, make sure that you are in degree mode as opposed to radian mode. So now I have these numbers. That's really helpful. So let's go back up here. Now think, what's our end goal? Our end goal is coefficient of kinetic friction, right? We can't get to our end goal without knowing the kinetic friction. So here's the trick. We're going to go back up to this equation, the net force in the x direction. So what I'm going to take a minute and do is I'm going to write down the things that we just determined. We just determined force of gravity in the y direction is equal to 666 newtons, and we determined force of gravity in the x direction equals 311 newtons. Down here at the bottom. So here's what I want you to think about. We know from up here that there is some net force in the x direction because the kinetic friction and the the force of gravity in the x direction are not equal to 0. So because that's true, let's go back up to the problem. We're given the fact that there's a net acceleration, so there's going to be an a net in the x direction of 3.6 meters per second squared. What we can do is you still know this equation, F net. So remember, we can write it like that, or we could write F net equals ma net, right? So if that's true, we know mass, up here it's a 75 kilograms, we know the net acceleration, So if we figure out what the net force in the x direction is, we will then know the net force in the x direction and the force of gravity in the x direction, which will tell us the kinetic friction. So let's take a minute and do the math. We have 75 kilograms times 3.6 meters per second squared, and that's going to give you 270 newtons. Now, here's what you're going to want to think about. This is the part where you really got to watch your signs. It's sliding down the ramp with an acceleration of 3.6 meters per second squared, right? So we set down as being positive. So if I have a positive 270 newtons for my net force, I have 270 newtons equals force of kinetic friction, which I don't know, plus force of gravity in the x direction, which is 311 newtons. So now to get the force of kinetic friction, I'm going to subtract out my 311 newtons, and I'm going to get the force of kinetic friction as being negative 41 newtons. So check your math real quick and think about this. If you have negative 41 plus 311, what do you get? 270. So we're good to go. So that gives us our force of kinetic friction. And that's good. It's negative, so that means it's opposing the motion. So if you remember, here's where we're at. The whole goal here is to find mu sub k. That's been our overarching goal this whole time. Basically what we've been doing is putting together pieces. So we found vector components, we wrote F-net equations, we found the force of gravity so we could find what our vector components were. Then we found our net force, used the net force and the force of gravity in the x direction to find the kinetic friction force. So now we're at a point where we know the force of kinetic friction is equal to mu sub k, or the coefficient of kinetic friction, times the normal force. We know the force of kinetic friction. Do we know the normal force? Here's the good news. We know the force of gravity in the y direction is equal to 666 newtons, and we know that the sum of the normal and the force of gravity is equal to 0. So if the force of gravity in the y direction is down, that means it really probably is a negative 666 newtons. So the normal force has to be equal to positive 666 newtons. So now I want mu sub k. I'm going to divide both sides by my normal force and get mu sub k equals force of kinetic friction, which is 41 newtons. And again, I'm taking out the negative because at this point it doesn't matter. I'm not going to get a negative. I shouldn't have a negative coefficient, and so this is really just about the magnitude, not the direction at this point. And my normal force is going to be 666 newtons. So now I should be able to divide. 41 divided by 666 newtons gives me 0.06 equals mu sub k. And what that tells me is the coefficient of kinetic friction between the box and the ramp is 0.06. That's good. We shouldn't have a unit because our newtons should cancel out. Okay? I hope this helps.